Hello guys, Assalamualaikum warahmatullahi wabarakatuh and a very good afternoon. So today I'm going to teach you how to operate the Design Expert version 12. So nowadays they already upgraded to version 13, but by right it's almost the same. So first you open the software so you can get the free version online. Then click Open Design. Okay. Open design if you already have a design. If you don't have a design, create a new design. So I will teach you step by step so you will not miss the train. After you click the new design, you're going to click the response surface. Okay, this is optional depend on your project. You can click to the mixture, or normally people are using response surface methodology, which is RSM. So they have a lot of choice. You can choose central composite, box beacon, or optimal. So most of my cases, my case study, I'm using central composite design because central composite design, the mean of central mean, I want to study the range of parameter whereby I'm going to put my optimized preliminary result at central. So I can see, for example, when I increase the time, at what time it will achieve maximum response and what time it will reduce the response. So that's the purpose for central composite designs. Means you're going to study at very minimum critical parameter and at very maximum critical parameter what happened to your response. That's the purpose. If you're not going to study at minimum and maximum parameter range, you can use either box beacon or optimal, depend on your design. Okay, first of all, what I'm going to do is I'm going to choose the number of parameter. So the numeric factor 2 means that I have two parameter. Okay, for example, my parameter is time because I'm going to study the deposition technique and also voltage. Okay, if you are using chronoamperometry, it is important to optimize the time and also voltage and put the unit time in second, voltage in volt. Okay, better put the real unit. So for time, I'm going to study from 100-second deposition to 1 minute, which is 600-second deposition. For voltage, I want to deposit from 1 volt to 1.5 volt. So I want to study at which potential is the best to get the response. In this case, I'm going to produce electrode for electrode deposition technique. Okay, so next is you can change this one, the option. Click the option and here is rotatable. I don't want rotatable because I don't want my parameter to be negative. So I'm going to have all the value is positive and click face centered. So next is the center point. You can reduce the number to 3. The minimum is 3, but I advise you just have bigger repetition is good. So the model suggested to do 5 repetitions. So you can choose either 5 or 3, depends on you. So I'm going to choose 5 and also face centered. Okay, then I click OK. So when I click OK, my parameter will fall on positive value only. If you click here, it's not centered point, which is rotatable. So vice versa will happen. You're going to have time in negative or even voltage in negative. It depends. So next, I click next. So here they're asking you how many response you want. Okay, in this case study, I'm going to study the deposition potential and time upon the response, which is specific capacitance. So my response is only 1. So I just going to specific capacitance and the unit is farad per gram. So just put farad per gram. Okay, so I'm going to stress you, unit and name should be real. Don't make a short form. Okay, if you have two response, for example, you also want to see the charge transfer resistance, you can increase this one into 2 and put here charge transfer resistance, the unit might be ohm. So depend on your study. Okay, then click finish. After you click finish, the design expert software will generate. You can see here 13 experiment for you. Depend on parameter. 2 parameter you can get 13 experiment. 3 parameter might be 20 experiment. So depend on your parameter. And as you can see here, 350 and 1.25 is a repeated value. This is a repeated experiment because we have 5 centered point. Means that we have 5 experiments that repeat to see the repeatability of your experiment and to validate your model, whether your model is good or not, to define or to get a good specific capacitance. So if you can get a lack of fit insignificance, means your model is good. So after you get this table, so you're going to do 13 experiments. You got the value and you're going to put all the value inside this box. Okay, so I already did the pre-elementary experiment, so I'm going to show you the box with the data. So I'm going to going to click here, file, going to open design. Okay, this trial one is also the same. This one no need to save. Okay, the same. Okay, this one. It's already the same, but I already did experiment with the fill box here. The response we already have the response by doing the experiment, and we calculate the specific capacitance. Okay, the important point is after this step, you're going to choose the analysis tab and click the response R1 specific capacitance analyze. Okay, double click on that. Then here transform, no need to transform yet, fix summary. Okay, from this tab, it shows you that this is your suggested model, which is quadratic, because you have the R square value close to 1, you can see. Then the alias model is cubic. So when you click the next step, which is model, okay, they already choose you to take the quadratic model. So no need to change. Actually, you can change, but just stick to the quadratic. Okay, next, Anova. This is the important thing. Okay, this is the tab where it explains your result. Okay, so I'm going to show you and to highlight the most important thing in this step. So make sure you pay attention. So the first one is the model should be significant. If the model is not significant, you might repeat the whole process. Okay, next, number 2 important things is lack of fit. Should be not significant. Did you remember the 5 repeated point? That 5 repeated point that you did in the experiment suggested by the design expert software is indicator to know the lack of fit, and it should be not significant. Okay, the tricks, I'm going to tell you the tricks. If you ask the question on the comment, I can give you the trick how to get the non-significant lack of fit. Okay, let's read more about that. Okay, they said that the model F value of 20.07 implies the model is significant. Okay, this sentence you can use in your paper. This is only a 0.05 chance that an F value this large could occur due to noise. P value less than 0.05 indicate model terms are significant. In this case, A square and B square are significant model terms. Means that we have two parameters. Parameter A time B potential. In this case, A square and B square are significant model terms. So you have a lot of model terms, A, B, AB, A square, B square. In this case, only 3 are significant, A square, and B square. So it's not, it's a good result, but it's not very good. At least you should have a significant model term A and B, because you want to see the correlation between A and B. In this case, your A and B is not significant, so you might do something about this model. So I will explain later about that. Okay, next is the lack of fit is good because it's not significant. Okay, so the lack of fit is good means that you repeat 5 times, so the result is almost the same. That's why your lack of fit is not significant. Okay, Next, we go to the R-square value. Okay, the R-square value should be close to 1 to indicate your model is good. And your predicted R-square must be close to the adjusted R-square. In this case, the predicted R-square is not as close with the adjusted R-square because the difference is more than 0. Means that the predicted and adjusted, the difference must be less than 0. Here is 0.6. You must repeat some experiment to get a better predicted R-square. So here means that the model predict the surface response for you, but is far off from the prediction. That's why some experiment might be repeat to get a good value of R-square. So the aim here to get all the R-square value close to 1. The value 0.8 and above is good enough. So in this case, predicted R-square is not so good. So we're going to repeat some experiment. Okay, this is the coded equation. You can see when we are using the equation and we put our parameter, for example, A is time, B is voltage, we can get exactly the value of specific capacitance. So you can also include the equation inside your paper. Okay, enough with Anova. So I repeat again, in Anova, the important thing is the model should be significant, lack of it should be not significant, and you must have a good significant model term here. 3 is not enough. You should have at least 4, which include the significance of A and B, the correlation between factor A and factor B. And number 4 is the lack of it. The lack of it should be not significant. And pay attention also with the R-square value. Should be close to 1. When the value is close to 1, it's good. Okay, move on to the diagnostic tab. Diagnostic tab we will learn a lot of behavior and find error in this tab. So for example, the first graph here, normal plot of residual, is good because all the data falls on the straight line, indicating the error is normally distributed. You are not going to see here heavy tail or heavy head. So this means that your experiment is good. Only certain experiment or certain parts needs to be repeated to have a very good result. Okay, move on to the predicted versus actual. From here, actually, you can know which sample is far off from predicted value. Here, you can see this is very far. The middle line is the indicator. If your sample fall in the middle line, means that you have a good track. So this is the range. Even your sample fall between the range set by the software. But as you can see here, click on that, and here after you click, you see at the bottom left here, please pay attention here at bottom left. When you click here, you can see this is run number 2. Okay, focus on the bottom left. This is run number 2. You should repeat run number 2. And also here, you should repeat on run number 10. I think you can repeat run number 2, number 10, or maybe run number 7. Only 3 experiment because it's too far from the center point. Okay, if you're not convinced enough, you can click to the other graph. For example, cook distance here. Click here. Okay, this is also run number 2. So this, we know that run number 2 is a problem. So you can see run number 2 and you can repeat that. And also here, run number 3 and run number 10. Okay, the others is run number 8 and run number 7. So the most obvious here, just repeat run number 2. And I suggest you to repeat maybe here. Run number 3 is also not good here because it's very far off. So maybe you can repeat 2 or 3 experiments. And after that, we're going to see the residual factor and so on. Last but not least, the important thing is to see the predicted versus actual. This is predicted versus actual value because this is we have 5 repeating sample. We should have a line then. Okay, this is good. The only bad thing is because this is too far off. You can see this is the, you must repeat this one and also this one. If you don't know this is from what, just click again with the cook distance here. This is run number 2 and also run number 3. You can repeat the experiment. Okay, then we want, even the graph is not so good, we have a little bit error here, but we can see the model graph. Click the model graph tab. This is 2D contour. As you can see here, this the indicator. The orange to red is the highest specific capacitance you can get, and the blue one is the lowest one. You can see that your specific capacitance concentrated on the middle, means that you actually successfully to see whether the interaction by increasing time of voltage, is it increase the specific capacitance or not. If you're not really sure, you can click all factor here. Click one factor first. Okay, you can see a good curve here, or you can click for factor A, means that you increase time. What happened that at one point it reached the maximum specific capacitance, and the specific capacitance drop if you increase the time. Okay, let's see factor B. The factor B also, you can see a curvature, means that the trend is slowly increase and decrease, is a good trend. So here is for the all factor. You can get a very clear comparison between factor A and factor B. Okay, now then we want to see the interaction. Okay, for the interaction, the best thing is to see from the 3D graph. Okay, this is you can see here 2D, and just click 3D surface. Okay, in response surface methodology, the more intense the curvature, means that your model is very good. In this case, model term A is significant, model term B is also significant, and you can also see from the curvature of the 3D graph. So it's very good. So to make the data more reliable, you must go back to the Anova and increase your predicted R-square value. If you increase this value, means that your graph is more reliable and your error might be more reliable and more good. Okay, let's say you have done the experiment. The R-square is now is okay, getting 0.8 and above. So you want to proceed on the optimization. So just click the optimization here, click the numerical. Okay, then you're going to set whether your time to be in range or maximum. So normally the parameter we put in range, potential also in range, but the response, we want to get the response the maximize that we can. So here, then we click here, the solution. Okay, here the model have only one solution for you. Means that when you repeat your experiment, you do the time is 403 seconds, potential is 1.3, you can get the maximum specific capacitance is 1105. So the desirability only 0.86, because we not yet doing the repetition on the experiment. We not correct the R-square value, that's why the desirability is low. Normally, if you have a good R-square value, the desirability will be higher, close to 1. Okay, so this is, I want to show you how to do the optimization. After you get the solution, you must repeat the experiment 3 times and calculate residual standard error. Means that, for example, you repeat 3 times, you get 110, 3 sample, you get 1100. So what you're going to do, 1100 minus the 1105, divide by 1105. So you want to see how many error your experimental value get compared to the theoretical. If your error less than 5% is a good enough, and the model actually can validate and can predict your surface response accurately. Okay, that's the most important thing to know from your graph, so you can get all the information for the optimization by that. And by then, I think I already have explained everything about the response surface methodology for you. So hopefully you success in your experiment. So that's all I think from me. So hopefully you can successfully implement the design expert software in your experiment. Okay, that's all. Bye. Have a good day.